Hey everyone, so in this section we're going to be talking about exponential functions. So let's jump right into what this would look like. So here's a quick example of an exponential function, 2 to the x. And so we know this is an exponential function because the base is a number. So this number down here is some constant number. And then the changing part is in the exponent. So the variable is up in the exponent position. So that's what makes it an exponential function. So in general, we have the following. An exponential function has the form f of x is, we can say, k times a to the x. And so k could be any number, and in this case a is the base, and it's going to be a positive constant. So we'll just say the base will go like this. The base is greater than 0. So we don't have negative bases for our exponential function here. And then the input is the exponent. So where we're plugging numbers in is the exponent position. So this is just some scalar or constant. So that's a number. Alright, so in general, we have this form for an exponential function. And these come up a lot in real life situations. So a lot of problems that deal with nature or populations have the form of an exponential function. So let's look at an actual example of a population of a country. Alright, so here is an example. This is the population of Burkina Faso, a country in Africa, and this is from 2007 to 2013. So we have the population in millions for each year, and then the calculated change between the populations in those years. And so notice that the change in the population amongst each year is different, so it's not constant here, and so that means it wouldn't be a linear function. So another hopefully kind of function models this, and it does. It's actually what we call an exponential function. And so this is just a visual for what would be happening with that population. And this nice curve going upward like this represents an exponential function or exponential growth. And so the formula for this population growth, it's right here, but let me just explain how you get this. So let's kind of break this down with this example. So let's suppose we divide each year's population by the previous year. So if we divide population in 2008 by the population in 2007, we would have 14.660 million over 14.235 million, and that would give us 1.03 if we divide that out. Okay, let's do that again for 2009. Population in 2009 divided by the previous year. Population in 2008. So that would be 15.095 million divided by 14.660 million. If you divide that, you're going to get 1.03. And so the fact that these both give us 1.03 means that the population grew about 3%, so about a 3% growth from 2007 to 2008, and then again from 2008 to 2009. And we can do that for the other years, and we're going to actually get the same value. And so what this means is that we have exponential growth. So we could say whenever we have a constant percent increase, so this is different than percent increase. This is different than if we had a constant rate of change. So the rate of change is these numbers here, and these are not constant. These are changing, are varying, but the percent increase is the same. So whenever we have a constant percent increase, we have exponential growth. Alright, so we had this formula here for the population. This is an estimate of the population being predicted since 2007. And so here's how you can come up with something like that. Recognizing that we had the same increase, 3% in the first 2 years, 3% the next 2 years, and we would continue to get 3% when we divide the population from 1 year in the previous year. So we can use that information to predict the population. So we'll say when t is 0, that's like our starting year, that's 2007. And so the initial, we'll call it projected. So we'll say projected population in 2007, so when t was 0, is really actually what we had to start with, 14.235. And so that is equal to 14.235 times that number 1.03. This is actually called the growth factor. So this number here that we calculated here, and we would have gotten if we continued calculating, that's called the growth factor. And so because this number didn't change, 14.235 stayed equal to 14.235, the exponent must have been a 0 on that one, because something to the 0 power is just going to be 1. So 14.235 times 1. Alright, so let me show you where I'm going with this. So t is 1, so that's 2008. The projected population, we have the actual population from the table, but using this model, the projected population would actually be 14.235, that starting value, times that growth factor to the first power. Okay, so that starting value times 1 of the growth factors, 1.03. And so if you plug that in, you get 14.662. So our actual value was 14.660 back here. So it's a little bit different, but when we plug in the numbers, but this is a very good estimate for this population using this format for our exponential function. So let's just do a couple more. So the next year, so 2 years after 2007, then our projected population would be equal to 14.235 times that growth factor twice. So it'd be like 1.03 times 1.03, or the fast way to write that is to the second power. And so that would give us 15.102, really close to what the actual population was, which was 15.095. We can continue to do that. Let's just do one more, just to have it here in our values. And so we have when t is 3, the projected population would be 14.235 times that growth factor 3 times, so to the third power, and that would give us 15.555. And so basically the way we came up with this formula here on the curve up here that I was talking about is just by using this recognition that each year we're growing by about 3%, and so we could say the population P in millions after the year 2007 is just 14.235 times the growth factor 1.03 to the t power. This is in millions. Okay, so this is an exponential function. Notice this is a constant in the front. It's just always going to be the number that we actually started with. This was k in our formula, and this is the base. So back in our original formula we called that a. So that's our base, and then t is our variable, and so we call that x in our last original formula. So this is just the variable t, and so that is an exponential function representing that population. Alright, so now let's generalize our exponential function, and I want to point something out that example was one where something was growing, exponential growth, but these are also used to represent exponential decay. So in general, we're going to say that P equals P naught times a to the t. Okay, so earlier we learned what an exponential function is, and I use the letter k here, but we're going to use P naught because it's a little bit more precise in talking about what happens when t is 0. So where P naught is the initial value. Okay, so it's like a starting point, initial value of your function. because it happens when you plug in 0 for t, because that would be a to the 0 power, which is 1, so just 1 times p naught. So it's basically the starting point. And then a is the we can call it like the growth factor. So a is the factor by which p changes, and that's for different values of t. And then two situations happen here. If a is greater than 1, we have growth, exponential growth, like that population example. So these are both going to be exponential, but this is exponential growth. Okay, so this represents something growing. However, a can be less than 1. It's still going to be positive, but it could be less than 1, and in that case, this represents exponential decay. So instead of growing, think of something as decreasing or decaying. So we call that exponential decay. And so it is still going to be a positive number, but between 0 and 1, just imagine like a fraction, like maybe 1/2 or 1/4 or something like that. And then one last thing to mention here in general, the factor a can be written as 1 plus r. And this is where r is the percent rate of change. So r, we'll say equals percent rate of change. I'll just abbreviate rate of change, but in decimal form. So we'll say as a decimal. So earlier, what this was 3%. So in that previous example, 3%, so 0.03. So it was 1 plus 0.03, which is exactly what we had up here, 1.03. So that's how you can talk about a. Alright, so now let's just briefly compare this to what we learned previously. So we had learned about linear functions, and so let's compare the two. So a linear function, and remember when you draw the graph of that function, it's a line. So linear functions, they have a constant rate of change. So it has a constant, and I'm going to abbreviate, rate of change. And so what we're talking about now, an exponential function, so an exponential function, it does not have a constant rate of change. Instead, it has a constant percent. So it has a constant percent or relative rate of change. Relative rate of change. Alright, so let's take a look at an example. So here's this example we're going to try. The amount of adrenaline in the body can change rapidly. Suppose the initial amount is 15 milligrams. Find a formula for A, representing the amount of adrenaline in the body in milligrams at time t. Alright, so right away we have an initial value. So P naught is 15 milligrams. And if you take a look at 2 out of the 4 of these, A and B are increasing by a constant and decreasing by a constant amount. So increasing by 0.4 constantly, 0.4 per minute, 0.4 per minute, those are actually both linear. So these two are going to not be exponential, these are going to be linear. And then C and D, they're increasing and decreasing by a percent. So that is going to be exponential. Alright, so just right away we are going to have 2 different versions of formulas here for these questions. So A, we need a linear function, and the initial quantity is 15, and so the rate of change is what's given in the statement, so that's the slope. So the slope is, or rate of change is 0.4 milligrams per minute, and then the initial value, that's like the vertical or y-intercept. So vertical intercept is 15. Okay, so in general with a linear function, we had we could call it like y equals mx plus b, or whichever way we want to talk about our lines. This is just one way to write it. We've also learned it like this, like f of x is b plus mx, but in either case, we can plug in these numbers. So we're going to call it a for adrenaline, and the initial value is the b, it's our intercept, our y-intercept, 15, and it's increasing, so positive slope of 0.4 times, in this case, t minutes. So every t minutes it's increasing by 0.4. And so that would be a formula for the function for 15 milligrams of adrenaline in the body initially, and then it increases by 0.4 after every minute. So part B is really similar. The difference is that because we are decreasing, the slope is negative. So just because the word is decreasing, we know that the slope is negative. So that's going to be A equals 15 minus negative 0.4t. Okay, so that's the only difference between letters A and B. And now C and D, here's our exponential functions. So C is increasing at a rate of by 3% per minute, and so the base, which is going to be a, little a, is found by doing 1 plus the percent. The percent is 3%, but in decimal form, 0.03. So it's actually interesting. This is the same value as the last example. That is just a coincidence. It's not always 0.3. So our initial value, P naught, was 15. And so our exponential function in general is P times P naught. P equals P naught times A to the T, excuse me. And so that's going to give us P equals 15 times 1.03 to the T power. And that would be increasing by 3% per minute. And now on D, where we're decreasing by 3%, in that case, think of decreasing, so we are actually going to end up saying, instead of 1 plus, the percent is like minus 3%, so it's actually minus 0.03. So that is 0.97. And so the formula for that would be P equals, still 15 is the initial value, 0.97 to the T power. And we just mentioned this, but notice that one of these is going to be a growth equation, the other one's going to be a decay one. This one's growing. Let me go in a new color really quick. This is more than 1. So this is A is greater than 1, so this would be growing. And then over here, this is less than 1. So this is less than 1, so this is a decay. So this would be decaying like this. Let's try one more example. So in this one, we have that wolves were once common in the western US, but by the 1990s, the population had been wiped out. And so in 1995, wolves were reintroduced to Wyoming from Canada. Starting with 14 wolves, their number increased to 207, and that was by 2012. So assuming the population was growing exponentially, find a function to represent this growth. And it's going to be an exponential function, and then t will be the years after 1995, and then we'll say what the annual percent growth rate is. So let's identify from the given information what we know. We know that we started out with 14 wolves, so that's actually P naught. We know another population value. We know that later, in another year, that P was 207, but we have to specify like for what t value that would be. So to be more specific here, P of some t value, okay? And so we know that t should be the years after 1995. And so this was the population in 2012. So if you just do some quick subtraction, that's going to give you 17 years, okay? So after 17 years, this is 207. Alright, so we have those two values, and now what we don't know is a. We don't know the growth factor here, the annual percent growth rate. And so using our formula for a exponential function, plug in everything we know. So I'll put it in colors, the things we know. We know that the population is 207, and that's when t is actually 17. We know the initial value was 14. What we don't know is a, so a is going to stay a variable. But like I just said a moment ago, this 207 is when t is 17. Okay, so these are all the things we know. So notice you have one equation and one unknown. So I'm just pointing this part out. This is an algebra fact for you. One equation with one variable, one unknown value is solvable. So if I would have had two unknown values, I would have needed two equations. So this is solvable. So that means we're good to move forward. Okay. So what we're going to do is we're going to solve for the only remaining variable, which is a. So solve for a. Alright, so what we're going to do first is we're going to try to get a isolated by dividing. So 207 equals 14 times a to the 17th power. And so I'll just divide both sides by 14. Okay, and so that's going to give me not a nice number. It's 14.785. It keeps going. So we're going to leave it as a fraction. So we have, so far I'm going to just rearrange. A to the 17th power is 207 over 14. So we're going to leave it like that. Now the one last step, how you undo a power like this, 17th power, is you take the 17th root. Okay, so like if this was a square, a second power, you would take a square root. If this was cubed, you would take a cube root. So on a 17th power, you take a 17th root. And so on the left side, that undoes everything happening to a, so that gives us a. On the right side, we leave that as the 17th root of 207 over 14. But you can rewrite any radical with an exponent if you make it a fraction. And so this is 207 over 14, and then the index right here in your radical, this one goes in the denominator of a fraction. So this is 1 over 17. So these are equivalent when you rewrite that, because really quick fact from algebra, just in case you need this in the future, the nth root of, let's say, a over b, it doesn't really even need to be a fraction. Let's just say the nth root of a. And then let's say there's a power here, m. This is a to the m over n power. Okay, so that's just in general how you can go from a radical to an exponent like that. So now we have a. So a is solved for. Let's go ahead and plug it in the calculator to get a decimal approximation for it though. And so let's see, we have 207 divided by 14, raising that to the 1/17th power. And so that's about 1.172 if we round. So a is approximately 1.172. Okay, so now our formula could be P, the population of the wolves, after T years after 1995 would be 14 times 1.172 to the T power. And so the question says, what's the annual percent growth rate? And so that growth rate is basically R in that equation. If you remember earlier, A was 1 plus R. Because the 1 in the front here, this is like the original 100%, and so it's growing by what's after the decimal point. So it's growing by 0.17. So growth rate is about 17%. And so that is it for this one. Let me tell you one more thing about families of exponential functions. Okay, so the last thing to talk to you about is families of exponential functions. And so here are just two examples for you. Here's a family of functions that's exponential growth on the left, and on the right, exponential decay. And so we mentioned this earlier on another section, that families of functions, they have something in common. So in this case, all, like, let's see, 1, 2, 3, 4, 5, 6 of these functions, they all have a base greater than 1. So remember, a is your base, so the base is greater than 1. And then all these ones that are decaying over here, they all have a base between 0 and 1. So that's what's in common about the families here. And so some things to notice is that if the base is larger, so 10 is the base here, 5 is the base here, then it's growing more rapidly. So the larger the base, you're growing faster. So something that has a base of 1.5, it's still growing. So notice that you still have growth here, but it's growing much faster with the base of 10. So the larger the positive base that's greater than 1, then it will grow much faster. And then over here, all of these are decaying, but something that has a value closer to 0 is going to decay much faster. So like this one here is decaying, something with a base of 0.95, but this one with base 0.1 is decaying so much quicker. So it drops down really fast and starts decaying really fast. And then one last thing to mention is this one right here. This is the number e. So this is the number approximately 2.718, and this is the natural number. It occurs in nature so much, in natural things, natural phenomena, that we call it the natural number. Sometimes it's called Euler's number. But if our base is e, so base e, we call it the natural base. Okay. And so as you can see, based on the number, the fact that I'm telling you right now it's 2.7 roughly, on the graphs, it's between the graph of 3 to the t and between the graph of 2 to the t. And that should make sense because it's between 2 and 3. E is 2.7. So it's between those two numbers. And so that one comes up a lot. And on your calculators, if you've never noticed it before, never used it, there is the button E on the calculator, which is representing this number, 2.718. Okay, so that is it for this one on exponential functions.